Okay, welcome to the review for the first midterm. You are welcome to bring to the exam an equation sheet. It's closed book. It's a 90-minute exam, and you'll have 4 hours to do it, from 8 o'clock until midnight. The official time is 8 until 9:30. You can bring a single equation sheet, double-sided, with whatever you want to put on it, a calculator, and a pencil. And those are the materials that you'd need. The material is the material for the first 3.5 weeks of classes. So it includes the first week, which was talking about fluid properties, pressures at a point, which we discussed in the second week, the integration of those pressures to look at the forces that are applied on structures, and also accelerating fluids, which was the first session of the fourth week. Specifically for the scheduled exam, the 3 questions that will be on that will be one that looks at viscosity and also buoyancy. A second question that deals with fluid pressures on structures and failures of those structures, so defining failure modes. And a third one also looking at fluid pressures on structures and including manometry. And so these are the various components that you need to review for the scheduled exam. The conflict exam does not conform to this, but certainly does conform to these 3 or 4 topical areas that are defined here. So what I'll do today is I'll just go through probably the full set of equations that you need to be able to solve the questions on the scheduled exam. In preparing for the exam, as I've mentioned many times, it's probably best to go back to the material that you have online. Previous exams especially, the format of this midterm will be the same as the one for the last 5 years, if not 10 years. We did some multiple choice ones in there somewhere, but these will not be multiple choices. So look at the last few years and you get some idea of the questions. I would say that if you know how to do the questions on those previous midterm exams, probably you'll be able to deal with the stuff that will be present on this particular one. Okay. So anyway, so I won't tell you how to review materials for the exam. You probably know that much better than I, but I guess go to the source of previous exams as the best indicator of what might come in the future. Okay, so what I'll try and give you is all the relations that you need to be able to solve the exam. So everything that was on this sheet will be the full set of expressions that you need. However, you need to know how to use them, and so I think that's probably the skillful part. So don't get too much bravado over the fact that, oh, I know this equation. You have to know how to physically use it. Okay, so for fluid properties, and we said specifically that we talk about viscosity. So we know Newton's law of viscosity is the idea that if you have 2 planes, one of which is moving at a velocity in the x direction, vx. So the slip lines between these 2 planes are like moving a deck of cards, as we've said. Then Newton's law of viscosity is that the shear stress that's applied on this upper surface, tau, reacting against this, I guess it would be actually it's the other direction, isn't it? Is equal to viscosity multiplied by the shearing rate, which is the velocity in the x direction divided by the gradient in the y direction. So y is vertically upwards in this. And so in this particular case, this length here would be dy. This would be dvx, the change from 0 to some magnitude of velocity here. And if you know the magnitude of dynamic viscosity, which is our term mu, which is units of Pascal seconds. Then you can calculate the stresses that are applied on a structure, or the stresses that have to be applied to shear it at a particular velocity. And so that's Newton's law of viscosity. And of course, if you want to know what the units are of this, if you know what the units of stress are, which are newtons per meter squared, and velocity and distance, then you can always calculate exactly what these component behaviors would be. Fluid pressures at a point. Well, we know that we have these generic relationships that if the accelerations are 0 in all directions, then we know that the change in pressure with elevation is equal to minus unit weight. We always choose for this a coordinate system which has z as vertically upwards and negative z as vertically downwards for this equation to be true. We know that if fluid pressures are in a liquid, then they would be linear. And so I guess before we do that, maybe we should just say what the other relationships are. We also know that the change in pressures in the x direction and the changes in pressure in the y direction are equal to 0. So these expressions are true for all fluids, be liquids or gases, compressible or incompressible. And if we want to get distributions of pressures at a point, then we can do it for the case where either the fluid is incompressible, so rho equals constant. If that's the case, then we can integrate this expression as the integral dp is equal to unit weight dz. And if we do that, we get the fact that pressure is equal to some initial pressure plus a change in elevation multiplied by unit weight. And so this height here is typically vertically downwards. We throw away this convention on z just because it's easier to do that. And this is always going to be the case in terms of defining the pressure at any particular location as a function of some reference pressure P0. So we're able to do that. If density is not constant, so this would be a liquid, and this would be a gas, then we know that because the pressure is related to density, then we have to be able to accommodate that. And in this particular case, the distributions of pressure that we would have would be something that would be curved. So certainly still it holds that the change in elevation and the change in pressure still conform to this behavior, but because density is no longer constant, no longer can you take it outside this integration and do it. Okay. If we look at going up and down in manometers, we have manometry. And so we have the so-called manometer rules, and those are that if you go up in a fluid, you subtract. If you go down in the fluid, you add, just as in this convention here. If you are in a gas, when you move up or down, the density is so small typically that you can assume that there's no change in density. And that if you're in an evacuated tube, then the pressure is equal to the vapor pressure of the material that's in there. We have to be a bit careful, I suppose, when we're dealing with fluid pressures, that we make some accounting for absolute pressure versus gauge pressure. Just have to be consistent in how we use that. And so we know that if we look at atmospheric pressure and absolute pressure, it's equal to 100 or 101 kPa, whereas in gauge pressure it's 0, with the consequence that if we look at absolute vacuum, then the gauge pressure would be minus 100 kPa. So we have to be mindful at least of absolute and gauge pressures in dealing with behaviors. Okay. If we look at pressures on structures, so let's do this. Then the pressures we have are controlled by three things that we'd like to be able to do. We'd like to be able to define the magnitude of the pressure. And also its point of action. And so the easiest way for us to do that is to be able to think of it in terms of this behavior that we have a plate, say, that's within a fluid. We're interested in that plate being defined. It can be any particular shape. It's just convenient to look at a rectangular plate. And if we define the centroid of that plate, for instance, and where we make sure that the fluid surface is aligned with the x-axis, so the x-axis fits on the top of the fluid surface, then we can define a couple of points. The first is that the height of the centroid below the water surface, wherever that water surface would be, is we define as being h sub c. We can define the location of that centroid in the plane of that plate as being the y-coordinate of the centroid, and the point of action of that force is defined as some length away from the surface, which is the location of the resultant force. And so in equating these, we can always get the magnitude of the resultant force acting on that plate. This is a generic relationship. It's equal to the unit weight times the area of that plate, which would be, and multiplied by the depth of the centroid below the surface. So h sub c is the depth of that centroid of the plate physically below the surface. Really what it's doing is it's taking two terms, the product of gamma and h sub c is just the average pressure that's acting at that point, or the pressure acting at that point, and then it multiplies that pressure by the area. Because it's an average pressure, then the product of the average pressure in the area gives the total force that's acting. The point of action of that force, so I guess this is F sub r, the point of action of that force, Y sub r, is given always by this relationship that YR is equal to the second moment of area relative to the x-axis divided by the slope distance to the centroid of that plate multiplied by the area plus the slope distance to the centroid. So physically this is saying that the location where this force acts, so in other words the location of action of this force is going to be, it's probably not so good, is going to be perpendicular to this plate. Just to keep on drawing, so this is an arrow that I'm trying to draw. So this is F sub r. It acts at this point here, which is below the centroid, always below the centroid, or can be equal to it if the upper surface intersects the surface. So it's equal to this location, which would be this, plus some small amount delta y r, if you like, which is this amount here. And so this is just a generic magnitude. We've done some examples. This is the depth of the centroid, and this is the area of the plate, which is A. This is always correct. It's a generic expression. And I guess finally, the other thing that we should be mindful of is often we're interested in defining not just the forces that act on a structure, but also, if you like, a failure mode. And that means that if we have an example that includes a geometry with a tank, we've done some things like this in class, where you have some kind of, I guess the other way of doing things is that if you're looking at a failure mode, then you have to take moments around a particular, even if you've calculated the forces that act on a structure generically, where you can take moments around anything, when you're looking at a failure mode, you have to define a specific mode in which it can fail. And so certainly you can get the forces and their locations by taking moments around any portion, but if you want to look at a failure mode, you have to use the pivot or the hinge that is defined to be able to resolve around that force. And so in a generic way, if you're looking at pressure distribution with depth, which would vary with depth, and you can always divide it into portions which are a uniform distribution and a triangular distribution. Then to be able to figure out the resultant of this, you can always take the fact that you know the resultant for this is going to be acting at mid-height. You know that the resultant for this is going to be acting, let me get rid of this, at this height. And if this is L, then this is definitely L 2L over 3, and this is definitely L over 2. But so if you want to take moments and find out the resultant of these, then you can always take moments around this point or around this point. If you take them around the top, then the total resultant of the system times YR is going to be equal to the resultant force on the square distribution times the lever arm on that square distribution plus the resultant force on the triangular distribution times the lever arm. So we know all of these. You know the total force has to be the sum of these two forces, and so we can solve for Y sub r. And that's fine. We can do that generically to find out where the location of action of that is. But if you take moments, if you're defining failure, then you want to define your moments around the particular locus of where that failure will occur. All right? So maybe more information than you needed. The other component maybe in terms of methods of solution, which you might look at. There are many different ways that you can solve these problems, and probably I don't want to confuse you by talking about them, but we certainly talked in class about the idea of having a generic gate which was 1 meter tall and 1 meter wide. water sitting above it, and this fluid being held back by this inclined gate. And so there are three ways that we could solve this. The first is to realize that on this inclined gate, we could just draw it as our inclined surface, where this x direction and this y direction are here, and we can get the force is equal to the unit weight times the area times hc, and the location of action is equal to this same expression we had before, where this is a standard result. And so we certainly know in this particular case where all those locations would be. So this would be the underside of this particular feature here. And so the centroid of this plate would be here. And so, oops. So this would be y sub c, and this would be can't draw it very well, h sub c here. So this would be that location at mid-height. So this would be h sub c, and this plane here would be this component here. So that's one way to be able to do it. The other way to do it would be to take this same geometry that we have here and to draw the fluid pressure distribution to the base here. We know that this is equal to some height, and so we know that this pressure here would be equal to unit weight multiplied through by this height, h. And so from this distribution, we could do exactly the same as we've done before. From the known solution, I guess we'd know that the resultant force would be the area under this distribution, and its point of action would be 2/3 along this length here, which I guess this length here is just square root 2 meters from this geometry. And so we could take, we know the point of action of this force and we know the magnitude, so we know both of those parts. So that's the second way to be able to do this. And a third way to be able to do this would be to draw the free body diagram. That is this geometry here. And look at all the individual components. And so the free body diagram would be something that looks like pressure distribution on one side that looks like this, a pressure distribution on the base that looks like this, and also the weight of this fluid from the area inside this triangle. And those would allow us to be able to resolve these, to be able to calculate both the resultant force acting horizontally, the resultant force acting vertically, the weight, and by resolving these we can come up with a reaction to these and the point of action just by taking moments around a given location. So the results from all of those are the same. And so certainly you'd never have something as involved in this in class, but it's good to know how to be able to, or on the exam rather, it's good to know how to be able to deal with these individual components in a straightforward way. And the final component is to deal with buoyancy. And so for buoyancy, we know that we can basically resolve forces, a tension that's applied on a cable maybe, a weight of the structure, if it has some weight to it, and also a buoyant force, which is applied. And that buoyant force is merely equal to the unit weight of the fluid multiplied by the volume that's displaced. In this particular case, a sphere or a circle. And that follows just generically from looking at the pressure distribution with depth. I guess if you have such a pressure distribution, then the basic idea is that if you look at the horizontal distribution, then the pressure acting at this point, if you isolate your sphere, not a very good sphere, but you could truncate the sphere just by drawing it as a square, and the magnitudes of the stresses that are acting are vertically downwards on this surface here, and a much larger force that's acting vertically upwards on the base. And it's really this mismatch between these two forces because of these two pressures that is equivalent to the buoyant force, no different than that. But you can always get the magnitude by looking at the fluid volume that's displaced and multiplying through by its unit weight. And that's it. Okay, good luck. Again, I think these are some notes that allow you to at least concentrate your mind on what might be important, but certainly there's no substitution for going back to the previous exams from previous years, looking at the format of the questions and being able to try and dream exactly what these the ones on this forthcoming exam might be. Okay, good luck. Thank you.